Hello, this is Professor David Farina. Today's lecture is on Chapter 0, Charting the Heavens, specifically Section 3, the motion of the moon. The moon and its phases. Many people have, from a very young age, known that the moon changes throughout the month. And most of you probably already know that the phases are what we call those different changes in shape. However, there's a lot of confusion surrounding the moon and how the phases operate. So today, my hope is to clarify a few of these things for everyone. First, the moon does not produce its own light. This is pretty obvious. However, where is the light coming from? Also is important to understand. It all has to do with sunlight, and it is sunlight that's falling directly on the moon. Now, when we have different phases of moon, we are seeing from the perspective of Earth, as you can see in this diagram, that the moon does in fact come up and is up at all points throughout the day, given a particular time of month. So for instance, during the new moon, the sun and moon are up in the same time in the same place in the sky. We only see the nighttime side of the moon in the new moon phase, and therefore we do not see the side that is covered in light, and therefore the moon that is in its new phase is not visible. But as the moon and sun move, from Earth's perspective, they move at different rates. The moon orbits the Earth, and as it orbits, the perspective that we get to see changes. And so by the next phase, the waxing crescent, which is right here, we get to see that the moon now shows a little bit of its daytime side. And that side is on the right. And we're going to go into a little more depth with this in a moment. And progressively, more and more and more, through the waxing phases of the cycle, we see more and more of the moon's surface, and it gets closer and closer towards our nighttime until finally we see the full moon. And the full moon is directly overhead at midnight. And from the point of full moon, we gradually start to lose or wane in the amount of light that's on the moon's surface. This time the light is on the left. And this is the dead giveaway that you're looking at a waning part of the cycle until finally we get to our third quarter, waning crescent, and then back to our new phase again. Something to consider also is that the moon is not at the same orientation from Earth to the ecliptic. The sun, the ecliptic, and its path are about 5.2 degrees from the moon's orbit, and so sometime during the new moon, the moon is higher than the Earth, and therefore its shadow is not cast directly on the Earth. And the same reason why during a full moon that the moon is below the Earth's shadow sometimes, or above, and therefore for these two reasons we do not have eclipses every month, which we'll talk about more in a moment. Now, I've added some more detail to this today to hopefully help you in your understanding. So I've added some more slides that are not from your textbook. So this is a little animation here of the moon and Earth and a fixed direction in space. And you can see, of course, that the moon goes around the Earth. That takes about 27.32 days to occur. And that's called the sidereal period of the moon, as compared to the stars, as we discussed in our previous lecture. So that's one way to look at the moon, is how long does it take to get around the Earth compared to the stars. But that does not really account for the fact that the sun is also casting its light on the moon itself to produce the phases. That cycle takes a little bit longer because, remember, as we discussed in the previous lecture, that the sun and Earth are not going to be lined up a month later. There's going to be some difference, some lag behind the sun, and as a result, one position of the sidereal period, the moon will get back to that same place as it was next to Scorpius, but the sun has moved on along the ecliptic. And so it takes a little bit more time to get from here all the way to where now the sun is to get to that next phase, to go from new phase back to new again. This is called the, as it says here, the synodic cycle. And this takes 29.53 days. I'm sorry if this covers up your ability to see here. Let's see if we can fix that. All right, well, we're going to have to reference those slides from D2L. And it's a little hidden here, but it actually takes about 1 month or month for this to occur. In fact, the name month comes from the moon. And so that's called the synodic period. Now, the phases of the moon can be seen throughout the month, and if you take a moment here, try to name those 4 at the top of the slide. You might want to pause your video here. Okay, and starting from the one right here, this of course is the waxing crescent. Next is the first quarter, then is the waxing gibbous, and then it's the full moon. So this is the waxing half of the cycle. And during the waxing phase, notice the light is on the right-hand side, and you're gaining light on the surface with each step. These primarily can be seen in the evening sky. So as we look towards the waxing phases, as it says here, new moon is invisible near the sun, and then this is the west. Okay, so as the sun is setting, if we were to watch over the course of the month, each day the moon would actually move backward through the sky, which is called retrograde motion, and it would be moving more and more towards the eastern horizon, which will be, when it finally reaches there, will be the full moon. So this first 2 weeks of the lunar cycle is called the waxing half. Now, from night to night, the moon moves approximately 13 or so degrees. And you can do the math on this, 360 divided by about 29 or so, and you'll get your 13 degrees of moon motion each day. Now, the second half of the lunar cycle can be seen during the morning sky. So, once again, this over here is in the west, and as the sun is rising in the east in the morning hours, the moon from its full phase will now wane, losing light. Notice the light is on the left now, and it's losing light until finally it makes it towards the sun again 1 month or month later. Now, one way to remember this, of course, is if you remember Karate Kid, hold your right hand up. If the light is on the right, you wax on. And if the light is on the left, you wane off. Yeah? Karate Kid. Now, something else I wanted to add in here is that the moon is tidally locked to our Earth. And what I mean by tidally locked is that we only see one side of the moon at any given time. The side of the moon that faces us, it does not change. It's always one side. In other words, the first time we ever found what the other side of the moon looked like was not until the 1970s when we traveled there with our Apollo missions. That's the first and only time that humans have actually seen it with our own eyes. And since then, it was only spacecraft and pictures that people are able to see that. So why is this? This has to do with the way that the gravitational forcing, the tidal forcing of Earth affects the moon. And so the one side of the moon is slightly heavier, and as a result, it's pointing towards us. As you can see, the distance here is pretty great. This diagram is not to scale at the bottom. And the little arrow, you'll notice at all points in the orbit, is facing the Earth, showing us the same exact side with each one. Now, it's also important to note here that as the Earth goes around, it does in fact rotate. It rotates one time for every orbit. I'll repeat that. The moon does rotate. It rotates one time per one orbit. So eclipses are also something that can happen. The lunar eclipse is something that you may have seen. If you've ever seen a moon in the night sky that looks very red in color, but it's not near the horizon, it's likely you're seeing a lunar eclipse. Now, a partial lunar eclipse is not something that you're going to easily see. The difference in the brightness is not vast. If you get lucky enough to see a total lunar eclipse, however, it's a pretty obvious red color. It looks like a bloody red color. So this image down here does justice to what a true total lunar eclipse looks like. Now, what's causing this has to do with the light from the sun is hitting the Earth. The Earth is producing a shadow, and the moon happens to be in a part of its orbit. Remember, we said they're about 5 degrees off in the orbit of the moon around the Earth compared to the ecliptic. Well, sometimes during something called a node, we can actually see the moon and the Earth and the sun line up in a straight line. Only during these special times, which we call eclipse seasons, is this possible. Now, you can see this picture here. We have an example. We've got a light source here. We've got a thumbtack. It produces something called an umbra, which is this darker shadow. And it also produces a penumbra, which is a surrounding lighter shadow. And this is caused by the fact that the light source has some width to it. And so some of the light is coming from this side of the light source, and it's producing a shadow on one side. And then the other side of the light source is producing a second shadow. So each of these are in partial shadow with each other. The umbra is complete totality, complete darkness, where the entire, the blocking light source here, which would represent the Earth in our lunar eclipse, the entire area is completely in shadow. So this is what it would look like with the Earth. If you have a partial eclipse, the partial eclipse might pass through the penumbra. In order to create a total lunar eclipse, it needs to pass through this central area, which is the umbral region. I'm sorry about this getting cut off. Once again, access the slides on D2O. So a total lunar eclipse can last upwards of an hour and 40 minutes in length, where we're in complete totality. It's definitely something to check out at some point. We did have one very recently that I was able to check out for myself. Unfortunately, it was a pretty cold night. But these are definitely worth checking out. So what's basically happening here is that the light is being scattered by Earth's atmosphere. Remember, it is in the complete darkness, but what happens is Earth's atmosphere actually can bend light around it, and you're getting light from the Earth's atmosphere being bent onto the moon's surface, and it, just like a sunset has that reddish hue, which is caused by the filtering of blue light, and the remaining red light shines onto the moon and produces this reddish color. If you want to check these two links out, this is the NASA Eclipse website, and specifically the Lunar Eclipse page for all future upcoming eclipses. Definitely check that out. There's typically 1 to 2 lunar eclipses per year, and as long as you're on the nighttime side of Earth, you can view them. Now, the other type of eclipse, of course, is the solar eclipse. I have seen a solar eclipse firsthand, and I will tell you that this is one of the most amazing, life-changing moments for me. I think everybody needs to see a total solar eclipse at some point in their life. You do need to travel for these, and we'll talk more about that in a moment. Once again, eclipses do not happen every month because, as this diagram shows, sometimes the moon is higher or lower than the Earth is compared to the sun, and as a result, they miss each other. But during these favorable for eclipses locations, these nodes in the orbit, we can have an eclipse. And in a total solar eclipse, we have the orientation of the moon between the Earth and the sun. Now, this is a number of eclipses that are going to be happening from 2010 to 2030, and right now we see there's a good one coming here in 2024, and it's going to pass right through Erie, Pennsylvania. Now, I would suggest going up to upstate New York, or maybe over here into Ohio, rather than going to Erie, PA, because Erie, PA is actually on the very edge of what we call this line of totality. And as a result, you're not going to get the best view by going to Erie. But upstate New York, or anywhere along this path, you want to get as close to the center path as possible. And you definitely want to do your research before you get there in terms of road conditions, orientation of the roads, something to definitely check out for that year, 2024. Okay, so solar eclipses are possible because the angular diameter, as we've talked about before, the moon and the sun are approximately the same width in the sky, about 1/2 of 1 degree, half of the width of your index finger. Now, because of this, the moon can cover up the sun during a total solar eclipse. And what happens is that the moon's light is blocked, and we get this path of totality as the Earth rotates below the moon, and as the moon passes by in its orbit, the moon casts its shadow, its path of totality, on the Earth. And if you're in this path of totality, this path of the total eclipse, you will see a total solar eclipse. If you're in this other part, the surrounding penumbra, you only see a partial solar eclipse, which is nowhere near as neat. Once again, I've posted a link to the NASA Eclipse website. Definitely you should check these out. Approximately 1 total solar eclipse happens each year, but as that previous diagram shows, you do need to travel for these. You can't not just wait for a particular time of day. You must travel to see totality. Highly recommended. So here are the steps. We've got first contact when the moon just touches the edge of the sun. We've got second contact when the moon gets over here. We've got totality. And during this time, we can see the outermost regions of the sun called the corona. And we can also see things like prominences shooting out from the sides. When I experienced this, you get noticeably cooler outside. Birds start to sing. Bugs start to chirp. And everybody thinks that it's nighttime in the natural world. And then just a few minutes later, totality only lasts a few minutes, the sun comes back out and it's the afternoon again. And it's like nothing ever happened. But definitely check this out. It's worth seeing. So we've got the chromosphere and the corona clearly visible. This is the only time that scientists can actually study the corona. It is very, very faint compared to the actual surface of the sun, which is called the photosphere. And also once again, you can see the prominences. Diamond ring effect's really neat. This picture shows the little diamond here, and this is like a ring. Looks kind of like a piece of jewelry. This is caused by a crater here that allows some of the sun's photosphere to pass through it, and as a result, we get this really neat effect. Something also to consider here, that the Earth goes around the sun, and that during this orbit, sometimes the Earth is closer to the sun, called perihelion. Sometimes it's farther from the sun, which is called aphelion. It says here eccentricities, the shape of the orbit. is greatly exaggerated. You know, the orbit is almost a perfect circle, but it's not quite a circle, and we've made this exaggerated to help you. Now, the moon also goes through a perigee, its closest position to Earth, and an apogee, its farthest position from Earth. And you can imagine how this would change the size of the moon and the sun in the sky, because they're at farther or closer distances. And so as a result, this can cause what's called an annular eclipse. So an annular eclipse is not a total eclipse, it's just because the sizes don't match up. So the moon might be too small and the sun might be too big, and all of a sudden we cannot cover the sun with the moon, and we end up with an annular eclipse, which looks something like this, where we can see the disk of the sun with the moon inside of it. And there was an annular eclipse in 1994, as this shows. And there's another picture of an annular eclipse. This one from 1984. Keep in mind, never look directly into the sun. You do need a special pair of glasses, like these solar glasses that became popular during the last solar eclipse. So you maybe even have some of these. You do need to use these in order to look directly at the sun. You could also use a projection technique like shown here. I've got a little solar projector to show you here. So the sun is projected onto a screen, and the screen is what allows us to see the sun. So the sunlight comes in, hits a number of mirrors, and is projected down onto this surface so that you can look directly at the projection. But do not look directly at the sun itself. We do have special telescopic filters that we can use. This is like a very, very good mirror, but if you look at the sun with this, you can actually use a telescope. You need to have the right tools. And finally, there are dedicated solar telescopes like this one called a Coronado, and the Coronado is specifically something called a hydrogen alpha solar telescope, which is a special type of light. So once again, conditions for eclipses, everything needs to line up properly. So you can see here's the node, and during an eclipse, the moon and sun are lining up, and the nodes are the place where the eclipse is actually able to occur. And here's what the region of eclipses would be. So anything around those nodes, it's possible to have an eclipse. But remember, the moon could be lower or higher than the Earth and its path around the sun, known as the ecliptic. Eclipses do happen in a cyclical pattern. They repeat themselves, so they're predictable. And it takes about 18 years, 11 days, and 8 hours for something called the Saros cycle, this repeating pattern that we were able to observe. And people for hundreds of years have been able to predict eclipses coming up based on the Saros cycle. And here's the basic way that we can plot this over time on a calendar. And this is just showing you once again how partial eclipses and the total eclipses and annular eclipses can occur. I hope you enjoyed our Chapter 0, Part 3, Moon Motions, and look forward to seeing you back again for Part 4. Thanks again.